going to talk about bit operations. And these are very low-level operations that let you manipulate the individual bits of an object. Usually, I don't know if you could use it with anything, but we are going to manipulate the bits of an unsigned integer. So you know that everything in the computer is binary. And so if you have some unsigned quantity, let's say that's 1, then you know that represented in binary, you have something that looks like this. And most of us are on 64-bit machines, so we have 64 bits here. And that's the binary representation of this unsigned integer 1. There's a series of bit operators that let us manipulate the individual bits. And the first one we'll talk about is the left shift operator. And inconveniently, it looks a lot like the stream insertion operator. So that's what it looks like. And the compiler can figure out based on context whether it should use the stream insertion operator or whether it should use the left shift operator. And so, for example, if I say cout, then it knows that cout's an output stream, and it's going to use the insertion operator. And then if I've got an integer or something like that, so for example, if I have I, because I is an unsigned integer, then it knows to use the left shift operator. And what I can do is, let's say that I want to left shift this 1 4 places. 1, 2, 3, 4. What I can do is just write 4 here, and that will shift the 1 4 positions from where it currently is. Now, and everything gets shifted. So if I had other 1s in that unsigned integer, they also would get shifted to the left that number of times. And then we get zeros padding on the right-hand side of the number. Now, I've shifted, but I haven't stored the changed number. One thing I could do is I could say cout, just to make this a little clearer, and you would get the number associated with a bit being on at that position. But I can also store the quantity back in I, and then I can cout I. I can also shift to the right. So if I wrote I is equal to I right shift 4, then in this case it would have taken my 1, 2, 3, 4, and so now the 1 would be shifted back to its original place. And again, in this case, we get 0 padding coming in from the right. So we get 0 padding. So that's how you can move bits left and right. And again, just to hit it home, if we had, let's say if I were 3 here, and now the number looks like this. And if we say I left shift 3, it's going to shift both of these 1, 2, 3. And so now these two positions would be 1, 1, 0, 0. We get padding in from the left. So then the next thing that we can do, there are a set of bitwise operators that we can use in addition to the shifting operators. So we have logical AND, we have OR, we have NOT, and then we have XOR, right? And this is exclusive OR. And the truth table for this is so exclusive OR is going to be, actually I should have written that here. Exclusive OR is going to be true when one or the other is true, but not both. So this is going to be 0 here, not both here, and then it's going to be 1 and 1. And so similar to their Boolean expression counterparts, but we're only using one ampersand, one vertical line for bitwise OR, and then for NOT, we're using tilde, and then XOR is the caret. And we'll see how we can use these to manipulate numbers. But what we're doing is we're applying these operators to the individual bits of an unsigned integer. So if we had something like this and we computed AND, it's going to compute AND on every one of these individual bits. And so the result you'll get will look something like that. So let's look at how, so the two main things that we want to do is we want to be able to turn a bit on and we want to turn a bit off. And so if we're setting a flag, then when something happens, we want to turn the bit on that corresponds to that flag. If we're adding an element to a set, we want to turn on the bit that corresponds to the element of the set. And so let's just look at this in terms of set operations, and we could, call this flag if we wanted to. And this could also be an unsigned. Well, let's go ahead and do unsigned. So of course initially we start with the empty set. And what I want to do is, let's say that I want to turn on a particular bit. So here's my set as it stands. And the way you do this is with something called a mask. And I'm going to shift a bit into the position that I want. So what this is going to do is it's going to create my mask. I start with 1, and now I'm going to shift it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so now I've got 1 here and 0 everywhere else. And there'll be a 0 there. And now what I want to do is I want to perform a calculation that results in 1. And then I'm going to store that 1 in that position. So OR gives us that operation. So I can say that set is equal to set ORed with the mask. I could have also said set So for these bitwise operators, you also have corresponding assignment operators, just like you do with multiplication and addition. So now after this, I can set, because I'm storing the result back in the variable set. Now I will have added this element to the set, or I would have set the flag that corresponds to that position. Now if I want to turn bits off, this is the other important operation that we need to do. Again, you're going to have your set, and let's just say, I've got unsigned. Well, I've already declared unsigned, so let's just go ahead and say, let's set to 6, and so this is going to be 0, 4 is on, and 2 is on, and 1 is off. So here's my set. And you're going to use the same idea of a mask. And let's say that I want to turn off this bit right here. So I need to put a 1 in that position, and that's going to be 1, 2 shifts. So if I shift 1 twice, then my mask looks like this. And now I need an operation that will be 1 for this, because I don't want to turn that bit off, and 0 for this, right? I need a bitwise operation that's going to give me a 0 for the bit where I, in the mask, but will be 0 for everything else, and that's what XOR does for us. So we can say set is equal to set XOR with mask, and that gives us a 1 here. We get a 1 here, and then we get a 0 here. So now, and I've successfully turned that off. And then of course I can also say set, because of my additional assignment operators. So that's the fundamentals of bitwise operations. We can use our left shift operator to create a mask, and then using OR we can turn bits on. Using XOR we can turn bits off. And in the next lecture we're going to see how to implement a set abstract data type using bitwise operators.